Here we introduce the viscous friction model, which is the viscosity in a fluid, and it causes this friction and it causes a force that's proportional to speed. Now this is just the opposite of our friction model, our dry friction model, in which the speed itself of the object didn't change the magnitude of the friction at all, but only the direction. In this case, our VREL term, which is telling us the speed of the object relative to the point of reference, will play both a role in the magnitude of the friction and also the direction depending on the sign of our VREL term. So let's set this up, solve for the equation of motion, and then solve for the state in this system. So first we define our reference frames and coordinates. And these are the same as in our dry friction model, where we define a reference frame I, because it's straight line motion, we only have one direction, and then we also have our coordinate x defining the distance between O and our mass m that's moving. Here's our damping coefficient and our damper, and then we have the direction of gravity. We set up our free body diagram of the mass, in which we have the force due to gravity. We have the normal force, which is acting equal and opposite because it's in static equilibrium. And then we have our friction force again. Our friction force, also defined here in a similar way as our dry friction force, but here we define our friction force as positive in the direction of positive velocity. And so we'll say that our friction force is pointed to the right. Now a quick note about the free body diagram is that when we apply this to Newton's second law, we're only concerned with motion in this direction, and using a viscous model, our normal force and gravity don't enter into this equation at all. However, for a free body diagram to be a complete free body diagram, you need to show all the forces, even if you anticipate not using them. So be sure that you create complete free body diagrams in all of your problems. Let's apply Newton's second law. F equals ma, and the only force that we're concerned about here is the force due to friction, which is in the positive direction, and we know that this friction model, F sub F, is equal to negative b and then v rel. The speed of our mass is equal to x dot, and then the point that we're referencing this to is going to be the attachment point on the other side of the damper. And so the speed of that attachment point is equal to 0. So our Vc is equal to 0, and then our VREL is equal to x dot. So now we insert this into Newton's second law. And so the only force that we have is negative b x dot, and this is equal to m x double dot, because our acceleration is x double dot according to this coordinate. We solve for our equation of motion, and we get that x double dot is equal to negative b over m x dot. So now to solve this equation for our state, we need to make a substitution. So x double dot is dx dot dt. This is equal to negative b over m x dot. And so now we have similar variables on both sides of the equation. We'll separate our variables, and this collects the like terms on opposite sides of the equal sign, and then we'll integrate. And for this we apply our boundary conditions. So at time 0 we have an initial speed, x dot at 0, and then at time t we have the speed x dot at the generic time t. We integrate both sides. So the left-hand side integral is the natural log of x dot, and then the right-hand side is negative b over m multiplied times t. We reduce the left-hand side to the natural log of a proportion equal to negative b over mt. And then solving for x dot, solving for the speed, we get this relationship in which we see here an initial speed at time 0, and then it decreases exponentially with a time constant of b divided by m. To solve for position, we're going to integrate both sides with respect to dt. And the boundary conditions here are from time 0 to time t on both sides. And with the integration, we get x evaluated from 0 to t, and this is equal to x dot at time 0. Remember that this is a constant, so we carry the constant through, and then we get negative m over b multiplied times the exponential e to the negative b over mt, that entire quantity evaluated from time 0 to time t. We evaluate this according to the fundamental theorem of calculus, and we have one term here on the end in which we have the exponential that's raised to 0. So that turns into 1, and then we evaluate this or solve for our position. And so here with our equation for position, we see that we start at an initial position that we define as part of our boundary conditions, and then we're increasing with this rate, but it's a decreasing rate of increase, and we see that with the 1 and then subtracting the decreasing exponential. So in the presence of viscous friction, we continue to increase the position, but then it eventually comes to a stop. So in summary, for our viscous friction model, we've applied a force that's proportional to the relative speed. And recall here that the relative speed is the speed of our mass relative to the point of reference, in this case defined by the dash pod or by this damper. If this were a fluid, say, moving in a tube, or a mass moving in a fluid that's in a tube, you would then take the relative speed of the mass to the side of the tube. This friction model, this viscous friction, comes in handy as we define characteristics of classic second-order systems and dynamics, because we begin to model these as spring, mass, and dampers all combined together. And you'll see that coming up.